Mixture distributions are very useful in statistics. For many of the recent machine and statistical learning tasks, we are interested in doing clustering of our observations, and discrete mixture distributions can come in really handy for doing that. For a lot of Bayesian modeling and Bayesian inference, we build Bayesian hierarchical models where our parameters for a probabilistic distribution themselves can also be random and follow some kind of probabilistic distribution. And in that case, the continuous and the discrete mixture distributions can be really helpful. Let's first discuss discrete mixture distributions. Consider a probability density of the form fx, which is given by the sum of k from 1 to large K of pi k times fk of x. Here, each of the pi k's is greater than 0. And the sum of all of the pi k's is equal to 1. In addition, for each of the k's, fk of x is a valid PDF. It won't be hard for you to show that fx, which is the weighted sum of the fk of x distributions, is itself also a valid probability distribution. We can see that the PDF is non-negative, and also it integrates to 1. So this is a discrete mixture distribution, where k is the total number of groups. Pi k is the probability that a random sample comes from group k, and the k ranges from 1 to large K. It should be large K here. And the pi k's are also known as mixing weights, which is the chance that a randomly sampled individual from the population belongs to group small k. And fk of x is the distribution of x if this person or this sample comes from group k. So depending on the group membership of the particular sample, the distribution of x will differ, and that difference depends on the group membership, small k. Let's see a concrete example about heights. Suppose that in some population, there consists of 55% women and 45% men. In this population, the height of a man in inches follows the normal distribution with mean 70 and standard deviation of 3. And the height of a woman follows the normal distribution with mean 65 and standard deviation of 2. In this case, if we let x denote the height of a randomly chosen person, regardless of gender, just from this general population, then the PDF of x is given by fx, which is equal to 0.45 times fm of x plus 0.55 times f of x. Here, the fm of x and the ff of x correspond to the two normal densities for the females and the males, respectively. So how can we draw in random samples from the discrete mixture distribution? To draw in random samples from a discrete mixture distribution, we can implement the subsequent two steps. Step 1, for each I between 1 and n, we randomly draw the discrete group membership delta I, which takes values between 1 and k with probabilities pi 1, pi 2, all the way up to pi k. After drawing the delta I, which is the group membership of each of the samples, in step 2, we want to draw the x accordingly. For each I, in step 2, we want to draw the x from the corresponding fk if delta I in the first step was sampled to be equal to small k. In other words, the distribution of x that we sampled from in step 2 will depend on which value we have drawn for delta I in step 1. As an example, let's try to draw 1,000 samples of heights from the former mixture distribution we have illustrated. Like we mentioned, we want to implement the two steps. Step 1, for all I between 1 and 1,000, we want to draw delta I, the person's gender, from the Bernoulli random variable with probability 1 of 0.45. What this means is that we want that the delta I to be equal to 1 with probability 0.45. So in this case, delta I equals to 1 will indicate that this person was drawn to be a male. And it's going to be 0 if this person was drawn to be a female. In step 2, depending on whether in step 1 this person was drawn to be a male or a female, we want to draw this person's height accordingly. If delta I was sampled to be equal to 0 in step 1, we want to draw xi following normal distribution with mean 65 and standard deviation of 2. If delta I in step 1 was drawn to be equal to 1, we want to draw xi following a normal distribution with mean 70 and standard deviation of 3. You can either write a for loop that implements this, which will be a little bit computationally burdensome, so it's not very efficient, or you can do the following with vector operations. So here's a code chunk that implements this discrete mixture sampler. We first sample the genders of the individuals. So we create a vector of length 1000, a 0,1 vector called gen. And you can see that the way we created it was by testing whether uniform 0,1 variables, so 1000 draws of uniforms, are greater than 0.55. I'm not going to explain this here, but you can check yourself that this is equivalent to implementing the inverse CDF method for the Bernoulli random variable with probability of 1 of 0.45. So the result of this should be a length 1000 0,1 vector, where the ith entry of gen is going to be equal to 0 if this person was drawn to be a female, and it's going to be equal to 1 otherwise. Now we've implemented step 1, let's try to do step 2. Before we start obtaining the actual samples of the heights, let's create two vectors, means and standdefs, which tells R what are the possible values, or what are the values for the mean and the standard deviations for each of the groups. So the means is a length 2 vector, because we have two groups here. And the first entry corresponds to the mean of the normal distribution we want to draw from for females. And the second entry corresponds to the mu for the males. Similarly for standard deviations, where the first entry corresponds to the SD of the normal distribution for females, and the second one is for males. After this, we can now implement the rnorm function and draw 1000 samples of heights. And note that depending on gen, whether it's 0 or 1, we want to use different mean and standard deviations. So when we draw the rnorm random variable and indicate the means and standard deviations, we can set the means to be equal to gen plus 1 and the standard deviations equal to gen plus 1 as well. And I'll explain what this means with the means as an example. So we know that gen is equal to 0 if this person is a female, and it's equal to 1 if it's a male. So gen plus 1 is going to be equal to 1 if this person is a female, and equal to 2 if this person is a male. And you can see that here, depending on whether this person is female or male, we're going to look at different entries of the mean vector, the means vector, when we do the normal sampling. So for example, if a person is a female, then gen plus 1 is 1. We will use the first entry of the means vector, so 65, as the mean that we use to generate the normal random variable. If this person's gender is 1, then gen plus 1 is 2, and we will use the second entry of the means vector, 70, as the mean of the normal distribution we want to draw from. And similarly for the standard deviations. So you can see that depending on Gen I, different mean and SD are going to be used to generate the height of the ith person. So let's take a brief look at the distribution of the samples we have obtained this way. Again, let's note that the samples we obtain are from the general population, so we are not conditioning on a particular gender. We can see that the mean of height is around 67, which is between the mean height of males and the mean height of females. So you can see in some sense, this is a blend and mixture of the two distributions. And now so let's take a look at the histogram of the height. You can see that this definitely does not look like a normal distribution. To start with, this distribution is skewed. And you can kind of see it to be a mixture of the males and females, where for the females, it peaks around 65 in height. And for the males, the height might be around 70, and the distribution probably looks like this. So before we move on to talk about the continuous mixture distributions, let's briefly mention why this procedure implementing the two steps actually work. So let's first consider the joint distribution of delta, the membership, and our x, the height or the mixture thing that we want to draw from. In this case, the marginal probability that delta is equal to small k, we know this is equal to pi k. And we also know that conditioning on a particular sample comes from the kth group. The CDF, or the distribution of x, can be described as large fk of x. So this is the distribution of individuals who come from group K. So from here, we can see that the marginal CDF, or the marginal distribution of a draw obtained using the two steps, which we denote by f large x of x, by definition is equal to the probability that large x is less than or equal to a small constant x. And if we apply the law of total probabilities, then we can see that this is equal to the sum over all case that this sample comes from group K, so P delta equals to K, and the conditional probability that P large S is less than or equal to X, given that this sample comes from group K, so delta is equal to K. And we can see this is equal to this, and this is equal to this. So this thing becomes equal to the sum over all case of large f k of x times pi k. If we take the derivative of this thing, we'll be able to see that the distribution of the thing we sampled from is going to be equal to the sum over all case of pi k times fk of x, which is the mixture distribution that we originally wanted to sample from.